Hi there, I'm Dr. McFerrin from DM Explains. In this video, I'm going to talk about phase lag compensation. Phase lag compensation is the opposite of phase lead. The structure of the controller looks very similar to phase lead with one small alteration. GC of S for phase lag is equal to K times alpha, that's new, times tau S plus 1 over alpha tau S plus 1. That second part looks just like phase lead, but in this case, alpha is bigger than 1. So this is, as I said, the opposite of phase lead. It causes there to be negative or lagging phase. So if I were to draw a very poorly done Bode plot of this is the magnitude of GC of J omega in decibels. And this is the phase down here. Then what happens is I've got a magnitude, and then at some corner frequency I'll start decreasing in magnitude, and then I'll flatten out at another corner frequency. The phase looks just the opposite of a phase lead compensator. It goes down. Pertinent information here is that there's a center frequency, omega m, and the value of phase at that is phi m. The first corner frequency is 1 over alpha tau, and the second corner frequency is 1 over tau. The characteristics of a phase lag compensator include that there is high gain at low frequency, which reduces the steady state error. This is somewhat equivalent to the PI part of a proportional integral derivative controller, so it looks like the PI part. The downside of this is it can have adverse effects on my phase margin, which affects stability. To try to avoid this, we typically will select 1 over tau far from the gain crossover frequency to not affect the phase margin. So let's look at our design procedure. I realize my writing is a bit sloppy, but that's why I'm verbalizing everything that I'm saying, so you get it in two modes of delivery. So the first step is to find K that satisfies the phase margin requirements. This is typically done by trial and error. Step 2 is to find the gain crossover frequency. That gain crossover frequency, omega pm, is found for K times G of S. Next, I'm going to choose 1 over tau to be between 1 octave. An octave is a factor of 2, so that would be 1/2 omega pm to 2 omega pm. And 1 decade, 0.1 omega pm to 10 omega pm. I'm going to select it to be between 1 octave and 1 decade above or below omega pm. Step 4 is to find alpha to meet the steady state error specs. And step 5 is to iterate as needed. Okay, so let's apply that to an example. I want you to design a lag compensator for a unity feedback controller, a unity feedback control system. If G of S is 1 over S plus 0.5, S plus 1, S plus 2. And I want this so that phi PM is greater than 25 degrees and the steady state error is less than 0.1 due to a step input. To solve this, I'm going to first look for K. To do so, I'm going to go to MATLAB and I'm going to try a couple of iterations here. So let's go over to MATLAB. So first I'm going to set up G. G is equal to the transfer function of 1, and then I've got the convolution of 1, 0.5 with 1, 1, and I need to then convolve that with 1, 2. Okay, close all those parentheses out. So So that's my transfer function. And then what I want to do is take the margin of some gain times G. So let's try, I don't know, 2G, margin of 2G. This gives me a phase margin of 78 degrees. That's certainly what I want, but I might desire to have a larger K. So let's go here, let's make this 4.5, get it pretty close. So what this does is this gives me a phase margin of 33, almost 34 degrees. So let's set K equal to 4.5, and this yields phi PM equal to 34 degrees, which is greater than 25 degrees. So what we usually want to do is we want to choose it so that way we get just above the requirement. The big thing to point out is we need the gain crossover frequency, and I got that gain crossover frequency to be 1.16 radians per second. So 1.16 radians per second is equal to omega PM. Then what I need to do for step 3 is to place 1 over tau between 10 times away and 2 times away from it. So let's say 1 over tau is equal to, I don't know, omega PM over 10. So 1 over tau would be 0.116 radians per second. That means that tau is 1 over that. Back in MATLAB we can calculate that. Tau is equal to 1 divided by 0.116. That makes tau equal to 8.62. Then step 4 is to find alpha using the steady state error. So I know that ESS needs to be less than 0.1. I know that ESS due to a step is 1 over 1 plus KP. So this is going to be ESS is equal to 1 over 1 plus the limit as S approaches 0. It's a type 0 system in this case, but it's going to be GC of S, my compensator, times G of S. So ESS is equal to 1 over 1 plus the limit as S approaches 0 of my compensator is K alpha tau S plus 1 over alpha tau S plus 1, and then I multiply that by G of S, so that's 1 over S plus 0.5, S plus 1, S plus 2. So let's evaluate this. I know that these S's all go to 0. This second term here just becomes 1, and so this is the limit as S approaches 0 of K alpha. I know that ESS has to be 1/10 or less than 1/10, which is 1 over 1 plus 4.5 alpha. So that means alpha has to be bigger than or equal to 2. So let's set alpha equal to 2.1 just to make sure. Then my compensator, GC of S, is equal to 4.5 times 2.1 multiplied by 8.62 S plus 1 over 2.1 times 8.62 S plus 1. Let's go back to MATLAB and see how this responds. GC is equal to 4.5 times alpha times the transfer function of tau, comma 1, comma, in the denominator I've got alpha times tau, comma 1. And then what I'm going to do is I'm going to take the margin of the series of G and GC, see what happens. Alright, so the result I get is a phase margin of 30.6 degrees. That's bigger than the 25 I was required to get. GM is still bigger than 6 decibels, which is fantastic. And by reducing that phase, you see there's sort of this bump that takes place between 10 to the minus 2 and let's say 10 to the minus 1. That's the reduction in phase as the result of my phase lag compensation. So the question is, will this hit the steady state error I want? To check that, what I should do is take the step. So let's come up with a new figure. and I want to step, and the way that I'll do this is I'll take the step of the feedback of the series of G and GC, and it says in the problem statement that it's in feedback with 1. Let's see what it looks like. Here is my step response. I said I wanted an error of less than 10%. When this settles out, it settles to 0.9. If my reference input is 1, then an amplitude of 0.904 is within that 10%, so I have met my requirement. If it did not meet the requirement, I would have to go back and try again. For comparison, I could also plot on this same figure the feedback of just G, and so we can see the difference in the steady state error that this makes. Okay, the second plot here now is red, and this one will settle out around 0.5, so the steady state error is 0.5 or 50%. So you can see what I've been able to accomplish using this compensation. The last thing to talk about before I finish out is just to point out that phase lead gives some of the benefits of a derivative, a proportional derivative controller. Phase lag gives some benefits of proportional integral, and if I want all of this together, I can couple a phase lead and a phase lag together into what I call a phase lead lag compensator. I actually made use of this type of compensator in my research work, although I was using it for specific frequencies and not so much the things that we're seeing here. That is all I have for this video. Thank you so much for watching. I'm glad to have spent this time with you. Hopefully I'll see you in the next video. Are you experiencing phase lag? You may be entitled to compensation. A non-attorney spokesperson is responsible for this ad. Montage, montage, montage. Ba, 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 ba. We've got cabin fever. We're going something bananas.